The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next speaker is Daniel Ortiz, and Daniel is from Santiago, Chile. His presentation is the repair of concrete bridges damaged in Chile by the 2010 earthquake. Daniel is a structural engineer by education. He's a contractor and a supplier and developer of sophisticated technologies in Chile. And I can also say that if you arrive in Santiago unannounced and call him, he'll take you out to a really nice dinner. So with that.
Good afternoon, everyone. Thank you very much, Peter, for your presentation. First I want to apologize because my English is not very good, so I'm going to try to do my best. This presentation is based in our experience making repairings of bridges in the area of the earthquake, and especially overpasses and also bridges over rivers. During this big earthquake, there were a lot of failures in bridges, mainly because some details, design details, like deficient connections between sub and superstructures, and also that produces mainly geometrical distortions in plan of the decks. And also other problems like failures because bars buckling, because inadequate confinement. I'm going to try to show you very quickly some damages in some bridge. This was a very typical damage in overpasses that were built recently using an Spanish technology, which is not really very. They don't use a really seismic design. You can see how big is the displacement of the deck, and here there were some stoppers that were destroyed when the deck moved to one of the sides. This is a failure in a shear pier where the vertical rebars were not confined. This is the same bridge, and you can see the spalling because that inadequate detail. Why damages happened? Damage resulted from insufficient integrity of precast concrete gated bridges due to the absence of diaphragms. The Spanish technique didn't use diaphragms like we used to do it in the past. Also, lack of constraint or rotation of deck in the skewed bridge, damaged piers and foundation, etc. The result was that the external girders suffered some damages in the webs and also in the bottom flange and sometimes in the upper flange. Here you can see some examples of failures because lack of diaphragms. Those are bridges in Santiago, which was 300 miles from or 250 miles from the epicenter. And this is a bridge which had failures in foundations, and that was located very close to the epicenter area. The repairing procedures that we carried out were mainly repairings of deck displacement, repairings of pre-stressed beam damages, and also substructure repairing and finally expansion joints replacement. First, I'm going to talk about the repairing of the deck displacement. The scope was to relocate the deck in its original position over the piers and abutments, which includes the replacement of bearings, expansion joints, and vertical connection bars. The procedure that we used was very simple. We removed the expansion joints, the vertical connection bars, the damaged concrete and pavement, and everything that could interfere with the vertical and horizontal displacement that we needed to get the structure back to its original position. So we had to use a vertical jacking procedure to lift the structure in one of the supports for proceeding later to the horizontal displacement. The jacks were supported on the beam supporting platform in bridges with concrete diaphragms or over steel brackets anchored to the concrete in bridges without diaphragms. Here you can see the two upper pictures. It shows the case where the jacks were on the beams platform. And in the bottom, you can see the jacks over steel brackets. We worked with enough 50-ton capacity jacks necessary to lift one end of the span. They were connected in serial using one or two hydraulic pumps to lift the bridge softly and uniformly in such a way that any other damage due to this procedure could happen. And lifting is just enough to be able to take the damaged neoprene bearing pads off and move the structure horizontally to return to the original position. In some cases, we used some temporary wooden supports to keep the structure in this position and lubricated steel plates between the girders to allow the horizontal displacement. Here you can see the pumps, you can see the jacks. Later, we needed to push the structure and to return to its original position, so we used horizontal hydraulic jacks to push the superstructure to that position. Once the superstructure was in its final position, it was supported again on the jacks, and all the temporary supports were taken off, and new bearing pads were installed, and the deck was finally taken down to its final level. Then new expansion joints, vertical steel bars, and pavement were installed, and in most cases, new concrete stoppers for horizontal movements were built. Now the structure was ready to be in service. This process took around, depending on the structures, usually 1 week to 2 weeks. Here you can see the horizontal jacks. And here you can see the installation, the change of the neoprene pads. The second case is the repairing of pre-stressed beam damage. Because, like I explained before, the external pre-stressed beams hit against the horizontal stopper and suffer damage in webs and bottom flanges, very close to their support, reducing their shear strength and affecting their support area. The idea was to repair them without having to replace the girders, reestablishing or improving their original properties without interrupting the traffic over the bridge, just restraining the traffic. The procedure was installing a temporary vertical support, removing all the concrete and rebars damaged by the distortions or failure, and cleaning up all the surfaces. Web and bottom flange concrete repairing were executed using two kinds of concrete depending on the size of the damage. And where the damage was small, we used some mortar with fibers, but when the damages were bigger, we mixed the same mortar with some kind of gravel. And in both cases, the bonding agent was applied on the old concrete surface before pouring the new one. Here you can see some damages in the web of pre-stressed beam and also in the bottom flange. The procedure was continue with injecting the cracks with epoxy, and And the webs were finally reinforced with using carbon fiber fabric and finished with a UV protective coat. So you can see the process here. We're measuring the cracks. This is the injection procedure. That's the same. And here you can see the installation of the carbon fiber. And this is the final. They look like brand new, really. Nobody noticed that it was repaired. The other job that we did was substructure repairing. The idea was repairing frame columns damaged by shear and torsion, and also shear walls like that bridge I showed you before. The procedure was cleaning and detection of injectable cracks, injection of crack using epoxy, reinforcement using carbon fiber fabric to improve strength and ductility, and finishing using UV protective coat. This is an overpass very close to Santiago, and central columns suffer some shear cracks because torsion. So you can see here the injection process and the wrapping with carbon fiber, and the application of protective coat, and this how that bridge look right now. In the case of shear walls, the process was a little bit more complicated. We have to cleaning and removal, and in many cases demolish all the damaged concrete and rebars, replacing of vertical rebars spliced with the old one, and also putting new horizontal rebars to improve the confinement. Finally, we apply a bonding agent in the old concrete surfaces. Finally, we cast repairing concrete or mortar, depending on the case. Finally, we also use a horizontal wrapping with carbon fiber to improve the vertical bars confinement and also shear, and in order to avoid rebars buckling and everything. Finishing, like in the other cases using UV protective coat. So here you can see the bridge and the damages. Here you can see the demolishing of the damages. The process of reinforcement and casting of the repairing concrete, and the process of wrapping with carbon fiber, and the application of the protective coat. And here you can see the bridge. Finally, we made a lot of expansion joints replacing many of the bridges that suffered horizontal or transversal displacement, suffered the failures of their expansion joints. So we had to replace that. Well, the process was very simple: removal of damaged expansion joint, clearing the area of dust and outside elements, proceed to cut and demolish the damaged surface, creating the space to apply the elastomeric concrete. I'm going to show some slides explaining that. Elastomeric concrete application with formwork in the noise blockout. And finally, installation of the neoprene extruded seal expansion joint. So here you can see the expansion joint damaged, destroyed really. So we took off those. We have to clean the surface and to create a new blockout. Here is the process. Here is the pouring of the elastomeric concrete, which is very, very fast. And finally, they are installing the new neoprene expansion joints. Here you can see the new joint, or the joint repaired. That was very, very fast. Usually one joint took a couple of days, the whole process. So that's it. Thank you very much.
Two questions. One is that, is there a report documenting all the repair work that has been done? Even if it's in Spanish, is there one available?
You're asking if there is...
If there is a report or papers where you describe the damage repair work that was done. Not the damage survey, but the repair work.
Well, really it's part of our know-how, and we have internal reports, but we can... It's the first time we are sharing our procedures, but anyway, we have internal reports, and if you want, I can give you some information about that.
I'll give you my contact information.
Yeah, okay.
And another question is more specific about shear keys. You didn't mention anything about how the shear keys were repaired.
How the shear
keys that you had stoppers at the end. At the
edges.
How were they repaired?
In the past, all the bridges in the country were used to have diaphragms. So in those cases, and in many cases, the platform, the support platform, had stoppers in the sides.
Yes.
Sometimes using some neoprene pads to give some additional damping for transversal movement.
Yeah.
So in those cases, and that bridges worked very well. But the Spanish experience, they didn't use the diaphragms. So when the bridges moved transversally, they hit the concrete stoppers, and the beams suffer a kind of flexure in the weak axle. So that's the reason, because they had damages in the web, obviously, and also in the bottom flange because of the heating.
Correct, but there was some shear key damages or some stopper damages in.
Oh yeah, because they were very weak. Really, they were more like an architectural detail than really a stopper.
But how
designed like a stopper. They were not shear keys, really.
Well, there were stoppers at the end that I saw.
Yeah, but they were more for aesthetics. No, really shear key.
Okay.
Now, all the codes have changed, and all the bridges, the new bridges has shear keys. Thank you very much.